No School of Mines.
You are going to Colorado School of Mimes? You
Yes.
would be a great mime. When I go to the circus, I love seeing mimes. Do you know what a mime is, Jeremy?
I don't.
A mime is someone that puts on white and black makeup and they can't talk, so they walk around and do things with their hands.
Okay.
That's called a mime. So you will make a great mime. Is that what that school's all about?
No, I've just studied like petroleum engineering. It's an
Oh,
engineering.
oh, you're not studying mimes. Okay, awesome. All right, so here we go, ladies and gentlemen. It's pretty good. I mean, it's pretty good. It's pretty good for lowbrow humor. I can do that pretty quickly. Ladies and gentlemen, I know that Isaac Newton is amazing. You know that Isaac Newton is amazing. Isaac Newton came up with this in the late 1600s. Man, is he my idol or what? So here's why I am throwing it to you this way. I don't think you guys have a prayer of remembering this. Some of you might. Some of you might have a prayer of remembering this on the AP exam. I think you probably have a better chance of understanding the process by which we get this. So, there. Because I know you guys all know, meow. I know you guys know that. So, let me explain to you the way Isaac Newton thought about this. All right? Isaac Newton thought, well, he did a little mental experiment. He said, what if I thought about all of the energy that was associated with the amount of energy I would need to get off of the planet? And let's assume that if I'm really, really close to planet Earth, then I don't have this energy due to my position in the universe, but I would have this final amount of velocity I need to get myself into outer space. And then once I was into outer space, I could go so far away from the Earth that I would deplete all of my energy and that was from moving. But I would have energy due to my position like we talked about yesterday. So because of Meow Mink, he figured out the escape velocity for the Earth. Does anybody know how fast you got to go to get off our planet? Woo! Maybe. It might be. It might be that fast. I know it's 7 miles per second. So 7 miles times 1.6, and then throw a few zeros on there. So, you know, it might be close to 7,000 meters per second. But that's fast, people. But it can be done. We do it all the time. In fact, that's how we got to Mars, let's be honest. So, Isaac Newton figured out that number, and look how tight it is. It's really 2g, the mass of the Earth, over r. That'll get you to where you need to be. Kepler came up with all these laws. All I want you to write, they are not going to test you on these laws. So flip your paper over onto the back. And all I want you to do to be a smart human being is know that his first law is called the law of ellipses. Okay? You know what? Planets don't go around the sun in circles. Planets go around the sun in an ellipse. And if you don't know what an ellipse is, it's kind of like an oval that you can put a circle in, and that circle can have a foci. That is an ellipse. Kepler was the first guy to say planets don't take this path, because that would be circular. Planets take this path, which is an ellipse, and guess what the foci physically is for the ellipse that planets go around? The sun is the foci. That was a big deal back in the 1500s, all right? Big deal. Don't need you to know that. See? Look, you can do it on a piece of paper, the same way in geometry class. Number 2, law of equal areas. Write it down. Write it down. That is the second law. Law of equal areas. Why was it significant to do a law of equal areas? Easy. In the late 1500s, they figured out that planets carved out equal areas in equal amounts of time. And if you go to the edge of those areas, you realize that planets go slower here and faster here. So you don't need to know anything about that. I just think it's good to be a human being that understands that planets speed up and planets slow down. That was such a big idea in the late 1500s, and we know why they speed up and slow down now. Even Cushy knows that. Cushy, why do planets speed up and slow down in their orbit?
I want to say like the inertia
inertia is the reason why they're in a circular orbit. But why would the planet be going slower out here and faster right there?
well, the faster one is closer to the upside.
So what's the sun doing to the planet?
Cooling off.
There it is, but they didn't even know what pulling was back then. They're like, what is pulling on this thing? We know it's gravity. See, I told you, even Cushy knows that. But back then, nobody knew it. That was an item up for discussion. Well, single-handedly, Kepler, from his research, came up with the law of orbital harmony. I don't want you to write anything into the law of orbital harmony other than this. There it is. That is the law of orbital harmony. It's pretty cool that you can put every single planet on a grid and get its distance from the sun and think about the number of years it takes to go around the sun. For you and me, this is a no-brainer, okay? We know that Mercury doesn't even take a year to go around the sun because it isn't very far away. We know that Pluto, a minor planet, right, dwarf planet, we know that its distance from the sun is epic. It's like 80 astronomical units, and every astronomical unit is 93 million miles. Look how many years it takes Pluto to go around the sun, a couple hundred, like 250 years roughly. So this is a no-brainer to us. Back then, don't ask me why, don't ask me how they figured it out. You can read books on it, it's pretty cool. They figured out that if you took the time for the Earth to go around the sun and you compare it to the time to any other planet, it's going to give you a number. Like 3.3. Gives you a number like 3.3. And you know what else equals 3.3? The distance it is away from the sun cubed compared to the distance another planet is away from the sun cubed. They actually squared the times, cubed the radii, and they came up with a constant to compare it to. We call that constant Kepler's constant, right there. How did he figure it out? With Isaac Newton's help. The force of gravity equals the centripetal force. Could you write this in a thread that looks like this? This equation went to that equation, went to this equation. And you are now in Roman numeral 11. We're almost done, as promised. Woo! This is a big deal. You take the force of gravity and you set it equal to the centripetal force because the force of gravity causes things to go in circles. And you knock out the mass of the planet because that's how algebra works. And then we're going to substitute in for velocity, right? There. You got to put a 2 pi r in where that velocity does. And you cross multiply it to find this time number. Look, t squared equals blah, a constant, to the r cubed. You end up with this Kepler's constant, which is independent of the planet's mass. They figured that all out, people. And it really helps us land on the moon, helps us do all the things that we want to do. It's pretty incredible if you think about it. That clear back then, they gave us all the mathematics to go to Mars and drop off some things, and then maybe do a little flying around Mars. Do you realize that we flew around Mars the other day? I think it was like 10 seconds. It was 10 seconds or 10 minutes. I think it's 10 seconds. That's all they did. They're just like, will this work? Yes. And now they're going to start really doing some flying around Mars. Speaking of flying around, we are flying through this stuff because we're not going to be able to memorize all the equations that are coming at us. What we're going to try to do is we're going to try to be able to think our way through these as we take the test with stuff we already know. For instance, if I want to know the orbital velocity of the Time Warner satellite that's providing me cable, all I've got to do is what I did on my last slide. Step 1, set the centripetal force equal to the force of gravity. Step 2, enter in the equations. As I enter in the equations, within that step, I will do algebra. Step 3, isolate for the velocity of a satellite and realize that I need the true value for r. Here's my satellite. Understand that that r is an r hat. That represents the distance from the center of the Earth up to here, and you'll be money when you're solving these problems. Okay? You guys will all be good to go. Any questions, everybody? Because it looks to me like we've got our satellite or velocity. Okay, so we've gotten through all this, and now the last little piece that I want to put in here is there. I don't have a space for that. I think you got to go underneath satellite orbital energy and maybe make your own Roman numeral there, which would be like Roman numeral 14. So go underneath satellite orbital velocity, and we need to have satellite orbital energy. And I think we already established once before that energy equals that work done. So the delta. How cool is that? I will not do example 3 today because I promised I would not turn this into a big festival of problem solving. But we will do problem 3 We'll do it on Thursday when we're all back together. Everybody cool with this? Mr. Mackey, I thought you already told us GMM over R, bro. I did. I'm just showing you another way you could solve it. Okay, that's fantastic. That is fun. Everybody is happy. You can pull out your Chromebooks, and I'm going to give you a chance right now to start the simulation. Yesterday we looked at the simulation, and then we said, oh, that's what I can do with it. That's what we're going to do for today. I'm just going to give you a chance to do that stuff right now. I don't want to blast through a bunch of problems right now. Now that we've got all the keys for how to do this stuff, then you are looking for that computer simulation. I don't care if you do that computer simulation in Camp. I know you have it as a hard copy, but you can also do it in Camp if you wish. Makes no difference to me. With that being said, let me escape out of this. I'm going to stop doing what I am doing right now. Let me get out of this slide. So RLA babies, are you getting what I'm saying we're going to do right now? Does it make sense?
Yeah. Dude, you gave us this paper yesterday, right?
I did. I gave you that paper yesterday, or you can find it in the week 32 assignments, Gravity Computer Sim. You don't need to hang out with me to do the Gravity Computer Sim. I'm okay if you guys log off. I'm going to stay here and hang out for a second, but if you guys want to log off, I'm down. It's no worries for me. I don't need to keep you captive. Your computer might run a little bit faster if you're actually not with me, but it's whatever you guys want to do. Okay?